So we just continue to develop our relationships as we use them in our studies here of RLC, now series and parallel circuits. So if we take a look at this example, determine the impedance of the circuit at the resonant frequency 17,794 hertz. You can see we've got a circuit here that's not a non-ideal circuit where we've got the winding resistance and the inductor in parallel with the capacitor. So as before, we calculate the impedance then, X sub L, 2 pi the frequency for resonance, and the inductor we get 894 ohms. Q then is calculated as X sub L by the winding resistance at 17.9. And notice that there's no units attached to it. When there are no units attached, we call that a figure of merit. And the impedance at resonance then, or the impedance where we have a winding resistance, anyway, yeah, a winding resistance gives us 16.1 k ohms. Back to the tank circuit. In most practical situations, an external load resistance appears in parallel with a non-ideal tank circuit. So we start to see these circuits where we hang a resistor on the output. That just indicates a load being applied. In terms of the actuality, that could be a speaker on a stereo. Obviously, the external resistor R sub L will dissipate more of the energy delivered by the source, and thus will have a lower overall Q, okay, for the circuit. The external resistor effectively appears in parallel with the equivalent parallel resistance of the coil, R parallel equivalent, and both are combined to determine a total parallel resistance. So we have our depiction here that says that the parallel total then is equal to, and those two little bars are telling us we've got RL in parallel with the equivalent circuit. The overall Q then, designated Q0 or Q0 for a parallel RL circuit, is expressed differently from the Q of a series circuit. So you can see the relationship here is saying that Q then in this case is equal to the equivalent divided by the equivalent reactance. As you can see, the effect of loading the tank is to reduce its overall Q, which is equal to the Q when it's unloaded. All right, special topics. Well, what are the special topics here? Bandwidth of resonant circuits. The current in a series RLC is maximum at the resonant frequency because the resonances cancel. The current in a parallel RLC is minimum at the resonant frequency because the inductive and capacitive currents cancel each other out. This circuit behavior then relates to a characteristic we call bandwidth. So now we can see here that in series and parallel resonant circuits, we've got a characterization here that starts to give us the what we call the F1 and F2. Those are above and below the resonant frequency, and that gives us a bandwidth. A certain series resonant circuit has a maximum current of 100 milliamps at the resonant frequency. What is the value of the current at the critical frequencies? So we can start to look at those to give us some idea of what the bandwidth is. So the current at the critical frequencies is 70.7% of the maximum. Okay, we can see here 0.707 times the current maximum. So I sub F1 on the low end is equal to I sub F2 on the high end, or 70.7%. In this case, we get a 70.7 milliamps. Okay, for a parallel resonant circuit, looks similar here. We've got the same type of representation, F1, F2 above and below, and it's again gives us 70.7. The formula for the bandwidth then is we take the difference in those two uppers and lowers. The calculation for the resonant frequency then is the sum of the lower and the upper divided by 2. So if we have a resonant circuit that has a lower critical frequency of 8K and an upper critical frequency at 12 kHz, determine the bandwidth and the center frequency, or the resonant frequency, for our calculation. So the difference, or the bandwidth, then becomes 12K minus 8K, which gives us a bandwidth then of 4 kHz. From that, we can also calculate then what is the center frequency, or the resonant frequency. F1 plus F2 divided by 2. So it's just like taking the average or the mean, 10 kHz. Half power frequencies, as previously mentioned, the upper and lower critical frequencies are sometimes called the half power frequencies. This term is derived from the fact that the power from the source at those frequencies is 1/2 the power delivered at the resonant frequency. The following shows that this is true for a series circuit. The same end result also applies to the parallel at resonance. So we have some maximum power equal to I squared R, okay, where the current is maximum. The power then at F1 and F2 then can be calculated in each case. So the power at F1 is equal to I squared at the F1 frequency times R. 0.707 squared R gives us 0.5 max. Okay, so the half power point. Selectivity then is the response of a circuit based on its frequency. Selectivity defines how well a resonant circuit responds to a certain frequency and discriminates against others. The narrower the bandwidth, the greater the selectivity. And we can see that in some of our depictions here of what's going on. Such is not the case, however. Those signals with frequencies outside the bandwidth are not completely eliminated. Their magnitudes, however, are greatly reduced. So this is where our half power relationship starts playing in. Another factor that influences selectivity is the steepness of the slope of the response curve. The faster the curve drops off at the critical frequencies, the more selective the circuit is, because it tends to respond only to frequencies within bandwidth. Some of this stuff is going to become really more beneficial to you as you learn other applications, like in the area of communications. So we can see here the generalized selectivity curve. You can see here that ideally we have this square depiction, but that's not really what happens. We end up with this roll on and roll off relationship. Q affecting bandwidth. The higher value of circuit Q results in a narrower bandwidth. The lower value of Q causes a wider bandwidth. The formula then for bandwidth of a resonant circuit in terms of Q then is stated as bandwidth is equal to the frequency resonant by Q. So you've got lots of relationships here that you can use for substitutions to solve for either the bandwidth, the resonant frequency, or the Q, and it can be substituted in other relationships. In this example, what is the bandwidth of for each circuit? So we've got two circuits, A and B. A simple series RLC. B is a parallel, okay, series parallel. So in this case, we're going to go through and calculate the center frequency. The center frequency, or the resonant frequency, 1 over 2 pi the square root of LC, gives us 1.6 megahertz. The reactive inductance then is 2.06 k ohms. So we can calculate the Q from that, 2.06 k ohms divided by the value for the resistor, 10 ohms. 10 ohms gives us 206 for our Q. From that, we can calculate the bandwidth at 7.96 kilohertz. For B, a little more difficult. We're going to use the full non-ideal relationship here because we have a winding resistance. Okay, although it's not marked RW, that we have a winding resistance. So we calculate using the full relationship. using the 1 over 2 pi LC. Okay, so in this case, they've let the value of the winding relationship be so small that we could approximate it by this ideal relationship. So we have 23.2 kHz. From that, we calculate the X sub L at 1.46 k ohms. Q then can be calculated from that at 14.6, and we get a bandwidth then of the resonant frequency divided by Q of 1.59. So again, go through this example and examples like this, work them out, make sure that you understand how to run these factors and these relationships through your calculator so that you can solve for the types of elements in these circuits.